Now we have Professor Mike Jennings from Swansea University. Professor Mike Jennings has been working in silicon carbide for forever. For almost
as long as you, Amador.
For almost 20 years. I mean, and also in another web and gap.
Tengo que volver a compartir, ¿no?
No, sí, la parte de
No, ya está.
Gallium oxide. Yes. He has a strong ties with the industry, no? Especially clusters in the region of waves, no?
Yes.
He ties on conductor information.
Yeah.
I don't know the problems.
Yeah, exactly. He's a.
I imagine something of this you will talk about.
Yeah, absolutely. I will talk about this.
And another thing is Professor Jennings will chair the next silicon carbide conference in Wales, no? The most important.
So in 2027, the silicon carbide conference will be in Newport in Wales. I think I'll be the general chair. We have a lot of work to do, but it should be really exciting.
Okay.
Yeah.
So
thank you, Amador.
Thank you for coming. Bye.
No. Thanks for the introduction. Okay. So let me just check. So first of all, thank you, Amador, for the introduction. I should say that it's a real privilege for me to come to CNN Barcelona and present, because when I was starting my PhD, I remember Jose Pepe Milan. He was a real pillar of the silicon carbide community, and CNN really defined a lot of the early work in silicon carbide device processing and technology. So it's a real pleasure for me to present here. So the title of the talk, as Amador kind of mentioned, I'm working not only in silicon carbide and GaN, and more recently gallium oxide. And I just want to introduce to you some of the work that we are doing in Swansea on the other ultra-wide bandgap and wide bandgap materials, GaN and gallium oxide as well, in terms of process technology. Okay. So first of all, I'll introduce myself, and I'll introduce the laser company. Yeah, I'll introduce our Centre for Integrated Semiconductor Materials in Swansea. Show you the facility. I'm sure that there'll be some interest in that. And then, a strong focus of ours in Swansea University is trench processing of these materials. Okay, we're focusing on trench because our feeling is that any device technology in power electronics eventually becomes a trench device, right? Because you want to maximize the number of chips on a wafer, etc., and minimize the die size, right? So everything will become trench in our view. So we're focusing on that. Then a nice section on gallium nitride, vertical gallium nitride, again, trench power MOSFET technology, as opposed to the conventional HEMT technology, high electron mobility transistors, that are typical in gallium nitride. And some of the early modeling work and experimental work on MOS interfaces of gallium oxide, and then I'll summarize the talk. So this is myself. Apologies for the photograph. I hope that doesn't scare you. But I started my academic career in Warwick University in England, and really in 2019, I could see that one of the biggest fab in the UK. The biggest semiconductor manufacturer in the UK is based in South Wales, in Newport. And at this time, it became an open foundry, right? And they were looking for technologies to commercialize. And we'd spent 20 years working in silicon carbide. So there was a real opportunity to take silicon carbide for us in the UK to the next level and start to commercialize it. They sponsored myself via the Royal Academy of Engineering grant, which was really nice because I didn't have to teach anymore. I could just focus on R&D. In reality, I still teach power semiconductor devices in Swansea. But then in 2020, recently, summer of last year, Vishay Intertechnology purchased that facility, and they are investing millions in this facility to turn it into an 8-inch silicon carbide manufacturing facility. So it works perfectly with my background, and so they have sponsored a 5-year position for myself, my chair. So I spend 3 days a week in the university, and 2 days a week in Newport, working with the silicon carbide engineers to bring this technology into manufacture, helping them as much as I can. In Swansea University, I'm head of power and energy, and these are the areas I'm interested in. Okay, so we've done a lot of work at the die level for reliability analysis of semiconductors, so TDDB, HTRB, so kind of qualification at die level for wide bandgap materials. Of course, I mentioned that the materials that I'm interested in, and the reliability, but mainly on the instrumentation side, which is quite interesting as well because I'm an electrical engineer. My first degree was in electrical engineering and electronics, so it's nice to bring that to the wide bandgap device side of things. Okay, and I line manage these guys, so we're not only about my area is obviously power electronic components, MOSFETs, IGBTs, and so on, but we have academics working right the way from up to power electronics, to power systems, and control. Okay, so we try to take care of everything, and they teach me a lot about circuits now. So this is the motivation for coming back to Swansea, as I mentioned. Okay, so this is Wales here. This kind of area here, this part that sticks out of the UK on the west side of Wales. England is here, and Warwick is around there, Amador. That's where we first met. But what you see here is what we like to call this. We have a very closely packed cluster of industry partners. Okay, from materials in the form of IQE and the Compound Semiconductor Center, which is a spin-out of or a subsidiary of IQE. They make epi, mainly GaN, epi wafers. And then we have obviously the big fab, right? Vishay, which is Newport Wafer Fab. They produce about 40,000 wafers a month, I think it is. So they're a high volume manufacturer, 8-inch of silicon primarily at the moment. But as I say, they used to do gallium nitride as well. But now they're moving to silicon carbide. And Microchip and the Catapult, which is a government organization like a Fraunhofer type institute in the UK, they focus on advanced packaging for power electronic devices. So getting the heat out and advanced packaging. So that, we have effectively the total chip supply chain, right? Yeah. So from materials to high volume production to packaging. And of course, the universities, Swansea and Cardiff, have just had huge investments. They're building massive fabs as well. Ours is the Centre for Integrated Semiconductor Materials. We focus on power, and Cardiff focus on high frequency. So they are very complementary. We're not repeating, yeah. It's not like a repeated investment. Okay, it's complementary. So we have a very strong ecosystem in South Wales, and as part of our New Horizon project, SAFEPOWER, we can leverage some of these industry facilities as part of that as well, which is exciting, right? So this is our facility. Okay, some pictures, but we have about 1,000 meters squared of Class 100 clean room. Okay, so it's ISO 567. So we have it's a big clean room for a university. Okay, Class 1000 it is, so not 100. We have 60 tools. Okay, and we're processing all of these materials. I'm not just going to read this list. Okay. But we process a lot of materials, but my focus is obviously wide bandgap materials, all right? And importantly, we're part of the UK National Facility on EPI, so we have an MOCVD reactor. Okay, my area is not really MOCVD or materials or EPI, right? But we have other academics that I work very closely with who are running this reactor, and it should be online within a couple of weeks, we hope. So maybe we can ask for your help there, I guess, right? So it should be really an interesting facility. But our real, as I mentioned, our speciality is in dry etch, okay, and plasma etching. And our link to SPTS and KLA, so KLA are a defect inspection company, a global company, but they are in the region now. And they've donated 4 tools to us to do dry etching of wide bandgap materials. So it's a really important relationship for us. And there's another facts and figures. So we have 12 staff, okay? And the way this was funded was 2/3 by industry and 1/3 from the government. So we got 30 million from the government and another 60 million from industry. So, you know, it's an industry, a government collaboration, really. And it's really exciting. And we're trying to get this clean room to work now. And it's taking time, but we're getting there. Okay, and, you know, these are the areas, okay, that in CISM, in the Center for Integrated Semiconductors, these are the areas we're working with. I lead the power electronics activity, but we have strong academics in semiconductors and healthcare, clean energy systems, and next gen over the horizon technologies like organic semiconductors. Okay, my colleague Professor Owen Guy, leads the healthcare side of things, and Paul Meredith leads these other activities in CISM, all right? And you can see, you know, our partners are listed here, okay? But we have a strong portfolio of academic funding and direct industry funding, okay? So the idea of the fab is really to prototype at wafer level, okay? So we're not processing pieces, we're processing up to 8-inch wafers and prototyping devices, even very ambitious, even in gallium oxide. You know, okay, there's no 8-inch wafers in gallium oxide yet, but, you know, wafer level, so 4-inch wafers, trying to process full wafers, get good uniformity, and demonstrate these technologies that are readily transferable into, say, somewhere like Newport, you know, into Vichy or into an 8-inch foundry. We also have a strong kind of skills initiative as well, and we're part of the Royce Institute. So we do clean room training for industrialists as well, right? So industrialists can come to our facility and get their hands on the tools and learn how different processes, the chemistry of the processes, and we also give them some seminars on the device physics, etc., right, as well. So yeah. Okay, so now we'll start the technical part of things, and hopefully you will come and visit us in Swansea as well as part of SAFEPOWER. So the first technical part I want to focus on is trench etch processing for silicon carbide, and specifically JFETs, okay? So this is junction field effect transistors, all right? And I'll explain a little bit about why that is in a second. Okay, so here's a device structure, okay? A JFET structure. So classically, traditionally in silicon carbide, the bottleneck for the technology, as I'm sure many of you are probably aware, has been the metal oxide semiconductor, the MOS interface, right? Which is really sensitive, defective, and really sensitive to high temperature operation. So our philosophy was, let's make life a little bit easier, okay? We'll try to do a junction field effect transistor, and, you know, that doesn't need a gate oxide, right? So it's a nice entry-level process for the fab, in my view. So this is the structure. So the way it works, okay, is you have a pillar or a fin, and the device naturally is a normally on device, okay? So you have conduction of electrons, right, between the source and drain. If you put a positive bias on the drain, right, you just get electrons going from the top to the bottom. But with a gate contact here, you can cut that channel off. So XJ here is the length of the channel, right? You can cut that channel off by controlling the PN junction, you know, depleting that region, okay? So by their very nature, JFETs are normally on devices, okay? And, you know, typically for modest pillar widths, so you can see the pillar width is defined by MW here, okay? I think M is probably meso width. But if you make that pillar very thin, you can change it into a normally off device, right? Because, you know, if this distance between these PN junctions is very small, naturally it'll cut off. In fact, we have a similar effect in 4H silicon carbide MOSFETs. If you planar MOSFETs, if you bring the cells too close together, right, you get a high JFET resistance. But you can achieve a normally off behavior by moving these pillars quite close together. All right, and that's our philosophy. And what I should say is that conventional, so these are commercial, okay? You can buy from Corvo now. You can buy JFETs, right? They're normally on, but they have this structure. And we reverse engineered some of those. And what we found is that the P pillars, so the P-type gate region is also present in the fin here, okay? But that's quite challenging from a processing perspective because you have to do sidewall implants and tilt. It's very challenging. So our philosophy is always to make the process as simple as possible to start with, right? To start. But what we quickly found when we were designing these devices, because initially we didn't understand why the sidewall implant here. You can achieve this truly just by depleting these regions as it is in this structure here, right? But what we found quickly is that, and I think this is very interesting for the audience, I think MOSFET technology and the limitations of power MOSFET technology in silicon carbide is very well understood, okay, and very well publicized, but not so well publicized in the JFET, okay, because JFET's a less common device, right, because it's normally on. But what we found is that, like the MOSFET, you get phenomenon called drain-induced barrier lowering, okay, in a JFET. It's like a short channel effect in a power MOSFET. So we found that is a limitation of this type of device. Also, the threshold voltage of such a device, okay, is very sensitive as opposed to a power MOSFET in silicon carbide. It's very sensitive to the doping concentration in the drift layer, because in a real silicon carbide wafer, some suppliers actually, I know this sounds unbelievable, but you can have a 20% difference, okay, in active carrier concentration from one side of the wafer to the other side of the wafer. So the doping control in silicon carbide of the drift layer is not as advanced as it is in silicon, for sure. And of course, that will affect the rate of at which this PN junction depletes, yes? And it will affect threshold voltage of your device, okay? So you get threshold voltage instability as well. So two things with JFETs are this drain-induced barrier lowering, I'll cover that in a sec in the next slide, and this this kind of threshold voltage instability of devices across an 8-inch wafer or a 6-inch wafer in silicon carbide. And if you look at the data sheet from Corvo for a device like this, they specify the threshold voltage. There's a big range, right, for the threshold voltage, and that's the reason for that. Okay. So what you see on the right-hand side of the slide here, okay, so obviously we did some device design to analyze this, some SRIM doping profile. So this is a box profile for the P-type gates. Okay, and what we were doing is, in the design phase, varying the channel length here and varying the etch, the etch of the pillar. So again, the etch technology is really important, to get nice sidewalls. Okay, so much like a trench power MOSFET, for this type of device, etching is a key process for this type of device, and control of that etch is very key. Okay, so we designed the P+, and what you see at the bottom here, okay, is depending on the channel length here, XJ. This is XJ. These different the breakdown voltage was very sensitive to this channel length. Okay, forget about edge termination at the moment. We're just looking at ideal structures here. Okay, so we're not even considering edge termination. This is a perfect, perfect parallel plane device, or should be. So we could see that even without any edges in the device, we were getting limitations in the breakdown voltage linked to that to that channel length. Okay. And my student Finn done a lot of good work on this. Okay, and what we noticed is that, as I mentioned, the larger channel lengths, were about 1,000, and the lowest was about 300. And what you can see here are 2D plots, okay, of the current densities at the onset of breakdown. Okay, this left left-hand side one is for a very low channel length, like 300 nanometers. And this right-hand one is for a maximum channel length, okay? And what we noticed is that, you know, this one was breaking down in the kind of channel region, right? Because the channel region for a JFET is in the middle of the pillar, right? Whereas the right-hand one was this is what you want, okay? Was breaking down at one of the edges, okay? It could have been this side, it could have been the other side as well, because don't forget that device is symmetric, okay? The only reason it chooses one over the other in the simulator is because the implant's based on a Monte Carlo type simulation, right? So it's a bit of randomness in the implant kinetics, which are modeled in the simulator. But you see that, you know, this is what we wanted to see, but we were seeing something like this. And we quickly realized that this is because of drain-induced barrier lowering, all right? And what you see is that, you know, if you plot the conduction band potential as a function of, you know, this is, you can see the cut line here, the X cut line, okay? So, you know, in this direction, we are cutting at X here. You can quickly see that the barrier to electrons from source to drain is much lower, right? Much lower for you know, for shorter channel lengths, yeah, for shorter channel lengths. And moreover, when you go to about 50 volts, you know, when you start putting high voltages on the drain, okay, and the gate, I should say the gate is minus 20 volts in these simulations because it's a normally on device, right? Yeah. When you go to higher drain potentials with the gate cut off, yeah, with the channel on, look at that, the barrier is pretty much non-existent, right, for a short channel. So this is a short channel effect that are inherent within JFETs, in fact, as opposed to conventional MOSFETs. You know, conventional power MOSFETs, you see a similar effect when you have, you know, source and drain too close and a channel which is very small. So this is something that we need to consider. And of course, it answered the question as to why, you know, commercial companies like Qorvo or you know, other commercial companies manufacturing these types of devices have a sidewall implant here, because if you include the sidewall implant, P plus implant down the edge here, by tilting your device during the implantation, you're effectively increasing the channel length of the device, right? So it's very interesting work, and we published this in Silicon Carbide conference, and we think it was quite unique because you know, most works focus on MOSFETs as opposed to JFETs. Okay, so that's one aspect. This is, as I mentioned, this is also another interesting study we did with the Compound Semiconductor Center, which are focusing on, they focus mainly on gallium nitride, but they were growing some silicon carbide epitaxial layers, okay? And, you know, the other type of work that we've done is developed code and software for wafer mapping like this, okay? So you don't typically see this in a university, right? You know, so as I say, we're working on wafer level technologies here. And this particular piece of research was trying to correlate device leakage current. So we fabricated, I don't know, a few hundred Schottky barrier diodes across the wafer, okay? And we were trying to match the leakage current to a candela map, yeah, of where the defects were in the wafer. And we got some reasonable success, okay? I mean, you can see some higher leakage currents in this region here, okay, which correlate to some defect map over here, okay? And likewise here, but we've got a bit of work to do on this. So, you know, our idea is, because if we can monitor wafer quality using electrical testing, it's a nice alternative to having a candela in the fab, right? But I think, you know, the issue we had here was the Schottky contacts in silicon carbide are particularly sensitive, and the barrier height of those contacts are particularly sensitive to the surface preparation And I think we can probably improve this correlation if we take care of the cleaning a little bit better in the future, or maybe use a slightly different cleaning recipe for the wafers. So this is something that we want to develop further, because we feel it can really help industry. Okay. Okay, and now our kind of flagship work is on silicon carbide trench power MOSFETs, trench etching. All right, and you know, I apologize for the slide here. I don't know what's happened there. But the issue, okay, with silicon carbide trench power MOSFETs is that you can see some cell images here of a trench power MOSFET. Okay, is that this blue is the oxide. This is the polysilicon green, but that corner at the bottom of the trench is exposed to very high electric fields at high reverse voltages. Okay, and it's much worse than in silicon, because you know the high critical electric field strength of these wide bandgap and ultra wide bandgap materials, all right, are a blessing, yeah, because you get lower on-state resistance as a result of that, and you can dope the epi more highly, etc. So you get the trade-off between resistance and breakdown voltage is better because of that. Okay. However, it's also the high field strength of the material is also a curse. Okay, and it's a curse because of this simple Gauss's law. Okay, in that the electric field transferred into the oxide, this is a product of the dielectric ratios between the semiconductor and the oxide multiplied by the high field in the semiconductor, right? So this field in silicon carbide is an order of magnitude, yes, higher than in silicon. So that means the oxide is also exposed to much higher fields. This number is about 3 times, okay, 2.53. So if you're operating at close to 3 megavolts per centimeter in the silicon carbide, okay, the silicon dioxide is operating at, you know, 9, right, megavolts per centimeter, and that's approaching the dielectric strength of the silicon dioxide, okay, the thermal oxide. So of course, in reality, you know, companies like Vishay, Infineon, they have patented technology, and in reality, they would put other structures like either another trench or a sidewall implant here to spread the field away from that corner. Okay, it's like edge termination in conventional power devices, but they're protecting the gates. Yeah. But for this study, okay, we didn't do that. You know, for us, because we're interested in it's more of an academic study, really, because we're interested in trench technology, we really wanted to understand how rounding the corner of the trench etch in a power MOSFET can relax that field. Okay, how much can we relax it? You never know. You might not need additional structures if we can have a thick bottom oxide here, say, and a high radius of curvature at the trench. You know, you never know, right? You might not be able to, might not need the additional features around that. You could simplify the processing, yeah, simplify the device process. So we did that here, okay, and what we did was this is simulation work initially, and you can see that, you know, for a higher radius of curvature, okay, at different high field points in the semiconductor, you can see that the effect that has on the breakdown voltage, right? And the higher the field, the bigger the effect. Okay, so it was really important. It's really important from the conclusion from this. It's really important to have a nice rounded edge there to relax the field in the oxide, even without these additional structures around the corner. Okay, on the left here you see that's just this equation implemented, okay, for different breakdown voltage in silicon carbide, and you see that's roughly 3 times that value, okay, in the silicon dioxide. So this was a good study, and we backed this up then with fabrication. So we use our tools to fabricate a nice sharp, you can see probably this image is the best here, a nice sharp corner versus a nice round corner, okay, and I think we use the deposited oxide in this case, yes, aluminium, 50 nanometers of aluminium oxide. That's the other thing to note when it comes to silicon carbide technology is that there's a trend to move towards deposited oxides rather than thermal oxides. You know, on the one hand, silicon carbide's advantage is that it has a native oxide, so you can grow thermally. But I think the classic approach these days seems to be a few nanometers of thermal oxide backed up by a deposited oxide. Like that seems to be the way it's going. So we focused on aluminium oxide, okay? And in fact, our partners at KLA developed this process flow, okay, in order to achieve the rounded sidewall. So you can see there's this fancy passivation here. They patented this, okay, and actually the masking and the subsequent passivation step here is quite advanced, okay, and so it's not so straightforward from a processing perspective to achieve a rounded etch. There's also chemistry involved, and this silicon tetrachloride chemistry is very important, but it's a combination of the chemistry and the process to create a nice rounded trench etch. And you can see on the top right-hand side of the slide the difference that made, okay? So all we did was make capacitors, made MOS capacitors, and check the breakdown voltage, and you can see it's about a 50% difference, yeah? This is the rounded trench versus the sharp corner. So you can see how important, the processing of the trench is for relieving long-term reliability effects on trench power MOSFET in silicon carbide. And rounded corners with high radius of curvature are vital, okay? Are vital because even if they don't, you're reducing the lifetime of the part by years potentially if you don't adhere to these kind of process rules. Okay, how am I doing for time? So another interesting field of study. So I'm jumping around, right? I'm giving you I'm trying to give you a nice overview of all of the work that we're interested in doing and are doing, without going into too much depth. So another area that we were working on in Swansea University and during my previous time in Warwick was on cubic silicon carbide. It's a really interesting material, cubic silicon carbide. It's a different polytype. Commercial silicon carbide is obviously hexagonal, 4H, okay, repeating after 4 bilayers. But cubic silicon carbide, okay, if you look at this diagram here, this shows the band offset between the semiconductor and silicon dioxide, okay? It's even better than silicon, right? So, I mean, Amador and myself were discussing this on the way here, right? I mean, this material for me is it's not as wide bandgap as 4H, so it's not going to have as good a trade-off between on-state resistance and breakdown voltage as commercial 4H. But in terms of gate oxide reliability and MOS interface quality, it should be much, much better, okay? And it should be very, very good for harsh environment application, niche application in harsh environments. And this work was also another Horizon EU framework project, which was trying to develop wafer technology for cubic silicon carbide. So cubic silicon carbide traditionally, which was seen as an advantage, was grown on silicon epitaxially. So you have a carbonization phase, right? And then you grow the actual silicon carbide epitaxial layer. And that was seen as very advantageous because, it's cheaper, right? From a commercial perspective, right? It's cheaper because you can have large diameter wafers, okay? But you do with a heteroepitaxy, kind of like in gallium nitride as well. You have different coefficient of thermal expansions. So in a real high power application, it's questionable, right, as to how robust that system is. Okay, so this project was about creating pools, pools based on seed sublimation and proper wafers in cubic silicon carbide, and it worked quite well. And I'll show some results from that in a second. But basically what you see is that, going back to this diagram, is that, you have a much, you can have a much larger electric field in the oxide on cubic silicon carbide before you get current injection, okay, into the semiconductor, gate leakage, basically. And that will be at much higher temperatures. because of this large band offset. And okay, that's one thing. And the other point to make here is that unlike 4H silicon carbide, okay, cubic silicon carbide doesn't suffer from the really high density of NITs, near interface traps. And what's not shown on this diagram as well is the near interface oxide traps as well. Okay, none of that affects cubic silicon carbide because they're only affected by these donor and dangling bond type defects. So your channel mobility, okay, and your channel resistance will be much, much lower for this system compared to 4H. And this is some work we did on just some capacitance voltage analysis, okay? Looking at different processing technologies, thermally deposited oxides, okay? And trying to optimize the interface trap density. But look at this, 10 to the power of 10. That's really low. That's a really low density of interface states. Okay, you never see that. I've never seen that in 4H silicon carbide, right? No matter what. And the way this is extracted, I think, was the high-low technique. I can't remember the exact technique, but whatever technique you use, okay, you always see a lower number. You always saw a lower number in cubic silicon carbide, so which is really quite unique and quite an interesting prospect for its future. Okay, so that's some of the work we did on cubic silicon carbide. Again, I don't know what's happened to this slide. My apologies. But the other interesting area, going back to the X, I probably should have put this slide a little bit earlier. But we focused, we've done a lot of work recently, and in fact, this paper was published in the recent Silicon Carbide conference in North Carolina, and it won Best Poster. So, we go to the conference for 20 years. It's taken me 20 years to win something, right? So this was a nice collaboration with KLA. So typically, silicon carbide wafers, okay, after you process the wafer, they are diced using a diamond saw at the end of the line. Yeah. So we thought, can we and quite often there's a yield issue. Okay, there's a yield issue. You lose a number of die because they shatter as the blade. You can imagine silicon carbide is quite hard and brittle, just a little bit softer than diamond. And then when you're cutting with a diamond saw, a lot of your die get damaged. You get chips on some of the die, right? So you lose some die based on that. And what we did was instead at the end of the line, okay, it's not perfect, but we deposited a nickel mask and used really deep plasma dicing in one of our Synapse tools, I think it was, okay, to singulate the die, right? And we demonstrated that we had a 14.4% yield improvement, okay, across the wafer. And also, we improved after the singulation, okay, we improved the kind of mechanical strength as well of the dies that were remaining, okay, as opposed to the dies that had been diced with a saw. So this is really interesting work for manufacturing of silicon carbide power devices. My feeling is that moving forward with this, we need to look at other masks other than nickel, because it's a bit of a pain, right? Having to remove nickel at the end, But this is a really exciting piece of work, which has had a lot of interest from our industry partners. Okay, right. So that's a little bit about plasma dicing. Now I want to discuss our work on vertical gallium nitride, right? So hopefully most of you will be familiar with conventional lateral high electron mobility transistor, okay? Conventional gallium nitride devices, which use a very high mobility 2D electron gas. So when you put this GaN, so gallium nitride with an aluminium content above GaN, you get a potential well, and you get a sheet of electrons, okay, at that interface, which have a very high mobility, okay, and they're very good for high frequency devices as well, okay. So the advantages of this type of structure, okay, you get a very low resistance between the source and the drain. These kind of structures with the buffer layers, okay, and the various epitaxies, including the P-type gallium nitride, to create an enhancement mode device, okay, a normally off device, are very, very common. Okay, you can buy these from, we can buy them from IQE, you can buy them from many next gen Japanese company, but you can get wafers very readily. These devices have pretty much instantaneous switching. Okay, so the current and voltage is not high simultaneously, so you can switch these devices very quick, and therefore they're very, very good for high frequency, and you get a very low gate capacitance and gate charge as a result. All right. However, the downside of this type of device is that if you want high voltage, okay, the drain and the source have to be quite far away from each other, because obviously the field is supported laterally in this type of device, yes, as opposed to vertically in conventional silicon IGBT MOSFET or silicon carbide MOSFET. Okay, so beyond, you will note that, there's commercial devices available in GaN up to about 650 volts, and the maximum kind of power rating is probably about a kilowatt. Okay, I mean, these devices are used everywhere now in laptop chargers up to 100 watts. All right, but if you want to push gallium nitride to work in a electric vehicle, for instance, you need very high power, very high current. Yeah. So 50 kilowatts to 200 kilowatts, you need high voltage blocking and very high current in the on state. And what that means is that the area of that die will be very, very large, okay, compared to a vertical power device. It's going to take up a big area because your drain has to be quite far away from your source, and you have to have multiple fingers, interdigited fingers, okay, to carry the current. So it's commercially unviable at the moment, right, to do that. So we thought, we have a trench expertise as well. Why don't we look at a vertical type architecture for GaN with a view to push it in terms of power rating, okay? And of course, it's very difficult to compete with silicon carbide because thermal conductivity of GaN is not as high as silicon carbide, right? It's much lower. And you can't readily, doping is not so easy either, okay? So we investigated this type of vertical structure with the P-GaN body grown epitaxially with our partners in the region. And of course, the advantages of a structure like this are it's a standard MOS gate, okay? You can use a simple IC to drive the device like you would with a silicon IGBT, silicon MOSFET, and silicon carbide is a little bit different, but you can use conventional gate driver circuits to drive something like this. With this one, you can't with a HEMT, you can't, because if you put too much voltage on the gate here, this Schottky diode between the P-GaN and the R-GaN will break. Okay, so you're limited in gate voltage on this on the HEMT, and you need a lot of extra circuitry around your gate to protect this. But we're not limited here. The blocking is independent of the lateral. The field is supported vertically, as we just discussed, so that's a real advantage. And it also has avalanche capability because we have a PN junction. This structure here, in fact, in a HEMT, the field isn't even supported by the GaN. It's usually supported by field plates, oxide field plates above the GaN. So if you break the device, okay, or if you exceed that field, it's like a capacitor popping, a capacitor will pop and it'll explode off the board. You'll see a similar effect in GaN HEMTs, okay? But in conventional devices like silicon IGBTs, silicon carbide MOSFETs, because you have a PN junction, you can avalanche, you can exceed the maximum field for a short amount of time and it will recover. It'll recover because it's a PN junction avalanche effect rather than an oxide breakdown. So that's a real advantage for driving inductive loads, okay, like a electric motor. That's quite advantageous. But of course, we lose a high mobility, okay? because now we've got an inversion layer, and it requires p-type doping, which is not readily available in GaN. Okay, we have to grow it epitaxially. So device is more difficult to fabricate. Okay, so we made some 200-volt devices. Okay, in our old fab. This was a number of years back now. We should be able to do better than this in the new facility once it comes online, right? But you can see the wafer here, and the structure is here. Okay, by all accounts, it's a vertical device. Okay, so the channel is vertical here. Okay, there's a P-body. Okay, and we have an inversion layer here. It's just that at that time we didn't have backside ground. We didn't have the technology to put the drain on the back of the wafer. So we collect. So we call it quasi-vertical because the current is collected, yeah, at the drain, which is still on the top of the wafer, right? But by all accounts, it's a vertical device, and you've got some of the parameters around here about the doping concentrations that we use. And this is what it looked like plan view. Okay, so you see the drain around the edge there, and the kind of source and gate in the middle part of the die. And we use a 2.5 micron drift layer to block the voltage for this type of device. And there's some initial characteristics. Okay, so we got some very nice classical output characteristics for the device for different gate voltages. Okay, we had a nice transfer characteristic, threshold voltage, a little bit high, and that's because it was quite difficult to control the P-body doping. Okay, so that's why the kind of, we noticed that the threshold voltage was actually quite unstable as well with temperature, because we think we're activating more of these GaN dopants, yeah, as we're increasing the temperature, or ionizing, I should say. But as a first attempt, this is a really nice device. Okay, we've got a threshold voltage 9 volts. A very nice specific on-state resistance and a reasonable breakdown voltage, giving us 90 volts per micron. Okay, so it's a very nice first attempt. What's not shown here, okay, is we extracted the channel mobility from the subthreshold, I think from the subthreshold characteristics. And, the mobility in the channel was about, at a first pass, was about 20, 25, okay? And when I think back to silicon carbide days, this is a first attempt, right? First attempt in silicon carbide, you were getting channel mobilities of about 5, right? So it's already like, almost an order of magnitude better, right? So we think that we can get very nice, actually, channel mobilities, of maybe approaching 100 in GaN. Okay, and finally, some gallium oxide work. At the moment, gallium oxide for us is still in the design phase. The slide's gone strange here again. My apologies. But basically, what my student is working on at the moment in gallium oxide is calibration of finite element models in commercial packages like Silvaco. Okay, and you can see that based on the classic semiconductor models for mobility, interface states, okay, unipolar resistances, we've managed to fit some experimental curves taken from literature, taken from this paper, with experimental output, transfer and breakdown characteristics. However, we need to show now that these are working with increased temperatures. As my predecessor said earlier in his excellent talk on gallium oxide, okay, gallium oxide has no P-type material. Okay, so again, we're looking at a very similar, and we decided to analyze another type, JFET type fin structure in gallium oxide. 1, because there's no P-type in gallium oxide, so you can't make an enhancement mode device. And 2, because we could benefit from a lot of the work we'd already done in silicon carbide, maybe, and transfer it to gallium oxide. So, and what the student looked at in this study was, in this structure, when you turn it fully on, okay, so we have, it's a MOS structure, as opposed to a PN junction structure. So this is a dielectric structure here. And we learned from our silicon carbide experience that we need a longer channel length, right? So we put the oxide down the sidewalls, yeah, like before. But what we learned is quickly understood is that when the device is hard on, okay, when it's fully turned on, you get an accumulation layer of electrons down the side. That's what this shows, down the sidewalls. So the accumulation mobility becomes very important for this type of structure. All right. And of course, we want to understand the geometry of the device. How thin do we need to make this pillar to get a normally off behavior? Yeah, to get a normally off behavior. And you can see here from the modeling work, you know, so he's matched his models in the previous slide. You can see here that, you know, we need a thin width of, so this is for a constant thin width and doping, okay? But you need, so say for a 1E16 doping, you need, you know, approaching 0.4, 0.5 to achieve normally off behavior and a positive. This is where the positive threshold voltage of the curve is, okay? So that's really important. Okay, and we also looked at similar effects, right? The drain-induced barrier lowering in gallium oxide. All right, same effect as it is in silicon carbide. Okay, but you can see here that you know, for smaller thin widths, okay, so the width of the fin, you get a much higher barrier height and much more likely to be normally off, you know, normally off behavior is advantageous here. Okay, I think I'm running over time, so yeah, sorry. So I'll skip this part. This is the last slide. So we also have done some practical work in gallium oxide on MOS interfaces because, you know, as I say, okay, there's no P-type, there's no MOSFETs, but you know, we need to understand what the quality is like. And we're in the process now of understanding how that affects accumulation layers rather than inversion layers, yeah, in conventional MOSFETs. So we looked at there's some processing details here, but what we found was that after some CV analysis as deposited, we can do a post-deposition treatment at 300 degrees C, and we get a lot less hysteresis. So we improve the impurity. You know, we can remove the impurities from an aluminium oxide layer. Yeah, so the dielectric was aluminium oxide. Okay, and furthermore, using high-low CV techniques, okay, we found that, you know, we reduced the interface trap density considerably after this post-treatment as well, by doing some extraction of the interface traps from the CV characteristics. Okay, so that's it. I'm sorry if I've gone on too long. So in summary, okay, hopefully we can if you're ever interested in visiting us in Swansea University, you're always welcome. We are open for collaboration, especially with the likes of CNM for device fabrication projects, okay, for sure. And I think we can really contribute in areas of wide bandgap trench etching. Okay, that's hopefully you understood that that's one of our strengths in Swansea University for sure. I introduced some JFET technology, okay, and the main conclusion from that work is that variable threshold voltage across a wafer and drain-induced barrier lowering must be considered for JFET technologies in silicon carbide, right? We demonstrated some vertical or quasi-vertical gallium nitride, okay. Questions remain over the actual critical field of the layers, but initial results were very promising in terms of channel mobility for sure, okay. We need to, and we're in the process of looking at P-type studies with Amador and colleagues, and hopefully during the course of SAFEPOWER we'll do more of this, right, for enhancement mode devices in gallium oxide. Okay. At the moment, we focus on depletion mode devices and demonstrated a JFET design, which is actually being fabricated now, and we showed that, you know, we can actually create nice dielectric layers on gallium oxide, nice capacitance voltage profiles with corresponding low interface trap densities, okay, with a post-deposition annealing of 300 degrees C in gallium oxide. So thank you very much for your attention, and I'd like to acknowledge, obviously, the SAFEPOWER project and all of our other supporters. So thank you. Thanks.
Thank you, Mike.
Thanks.
Time for quick question, no? Because, okay. Thank you for your great presentation.
Oh, no, it's a pleasure, Ando. Pleasure.
Thank you very much. And I have two questions. First is if range MOSFETs, silicon carbide, are improving and you try to manage all these issues and electric field power, etc. Do you see some interest on the pure JFET still? And if yes, in which application for ranges, etc.
Sure.
And second question concerns the plasma etching. You mentioned very nice also.
Yes.
But this I mean, you completely separate the dyes by plasma.
Yeah. There
is any auxiliary process only by plasma. And then is there any, for example, if you don't have nickel as backside metallization, you need, for example, backside metallization finish with silver or gold. Is it possible to make the dicing using your method?
Yeah, good question. So I'll take the first one first about the JFET, right? So in terms of JFET demand and application, right? I think so the project that we presented here was sponsored by a company called Bones Semiconductor. So JFETs are popular. Silicon carbide JFETs are, they're looking, there's a high demand for server farm protection devices, okay? So solid state circuit breakers, because it's a normally on device, usually allowing power to be delivered to the server farm. And you need some auxiliary electronics. If a high current or a failure is detected, you then apply the voltage to turn the device. So it's much quicker, right, than a typical galvanic valve here, circuit breaker. So that's one area that's a lot of interest in silicon carbide JFETs and why this project was funded. The second, you've got companies like Qorvo. So the other interest in silicon carbide JFETs is for cascode devices, where you put the JFET in series with a silicon MOSFET, okay, and you convert the normally on behavior to a normally off device. So again, the application areas, maybe automotive applications, but Qorvo, for instance, I think sell modules which have cascode JFET and silicon carbide devices. The issue, of course, with as I mentioned, with silicon carbide JFETs is I think they don't have a very high yield, right, in the fab because of the variance in doping across the wafer. So I guess that although the process flow is simpler, right? The process flow is simpler for a JFET compared to a MOSFET, but I guess they suffer with yield issues, and they don't tend to sell normally off enhancement mode JFETs because I think the pillars must be very small, on those mesostructures. So I think they're mainly using cascodes and for circuit protection JFETs. So the second question about the plasma dicing is a good question, and we do have more work to do on that for sure. It's not ideal. I think that the wafer is totally singulated just based on a plasma. There's no other process. I'm sure they singulate the device just using the plasma, right? But as I mentioned, it requires a nickel mask. Whether that is compatible with with a thick, if you've got thick silver layers and gold layers on the bottom, I think this is the issue, right? We need to investigate that further. Look for maybe, can you do this with a BPSG, or can you use a different mask, right? Which is easier to remove, and etc. So I'm not entirely sure. I think this was just done on a blank wafer, Okay, I'm not sure if it was done on an actual device rate. I think it was, but I need to check that. I need to check. I can't remember. So my apologies for that one. But yeah, I'll check. I'll ask the guy. Yeah. Any other question?
So yeah, we are on time or?
We are on time.
Okay,
Go,
so.
go. If there are more questions,
Okay.
go ahead.
I think you have explained everything very well, so.
Right.
Maybe I have one very particular question. In the very last result you showed about the capacitors, yes, please.
Yeah.
I missed the thickness of the layer.
50 nanometers. 50 nanometers.
50.
About. Sorry, I said something happened to the slides. The slides, but yeah, it was.
I see here also that the maximum capacitance looks like it's growing. I mean, looks like if it's
Growing.
leaky, it's a leaky capacitor, right?
Yes, because it's not. You would expect this. So this is an accumulation, okay, right?
Yeah.
And inversion, you would expect transition to be a lot sharper, right? I think it's because if you have a large interface track density.
No. I mean, in the saturation regime,
Yes.
you should expect flat.
Flat, yeah.
So
It's
it
leaking.
looks like it's a
Yeah.
leaky.
Of course. I mean, we've got a lot of work to do to perfect the process for sure. This is one of the very first attempts, right? So, no, I agree. We need flat accumulation, and we need, ideally, a sharper transition into depletion, and inversion. But, it's probably not really going into inversion either, right? Because it's a wide bandgap semiconductor. It's probably just, and it's the capacitance is continuing to decrease, which really indicates deep depletion, in fact, right? So I don't think.
No, that's when it was missing the frequency.
Yeah,
it's high frequency. curve.
Megahertz. Yes, 1 megahertz. Yeah, absolutely. Yeah, sorry, I could improve this slide massively. Yeah, it's a one megahertz. Yes, yeah.
Thank you.
No problem.
I have to answer, two questions for you. I mean,
Sure.
what do you think about the reliability problem of the gate oxide on gallium oxide? It's gonna be worse or better, or what is your opinion? And the other slide with Xavier comment is as we cannot make MOSFETs right now in gallium oxide, which is the future we expect with JFET, if it's a possibility, or which would be the field which is not covered by silicon carbide, complement, whatever.
Yeah, very, very good questions, Amador. Yeah, for sure. I mean, on the face of it, when you think about gallium oxide, is a much higher critical field than even silicon carbide, right? That means that, for trench devices, the field in the aluminium oxide is going to be much higher again than even in silicon carbide. So for sure, there's going to be issues in terms of reliability, for sure. The other issue for me with gallium oxide, in addition, to the reliability issue for the future is, the bulk mobility is only 300, I think, right? In gallium oxide.
Well, being very optimistic, I think the maximum is below 200.
Yes, yeah. And for me, don't get me wrong. I'm a big advocate for gallium oxide, and it's an exciting field for sure. But for very high voltages, okay, if you're talking about 6.5 kilovolts, 10 kilovolts, really that is territory that's not even occupied by silicon carbide at present. It's occupied by silicon IGBTs and silicon thyristor technology, and they are strong. They're bipolar devices, right? Because you have a very thick drift layer. Okay, if your mobility is also small, you can't really use unipolar device, right? So for high voltage devices, so I'm trying to get to your question about what type of device architecture, right? So for me, for high voltage gallium oxide devices, we're going to have to look at a way of injecting minority carriers into that very high resistance drift layer. And that's going to be based on heterojunction, yeah, or something along those lines. That's my feeling, right, for gallium oxide. And of course, I think Edgar's alluded to it earlier. It's really low thermal conductivity, so I think wafer thinning technology will be very, very important for gallium oxide and advanced packaging for removal of the heat. And that will also exacerbate the issue with any sort of gate oxide reliability, right? Because these failure mechanisms in silicon carbide, it's, with a small band offset between the silicon dioxide and the silicon carbide, the failure of that interface is exacerbated at higher temperatures, right? And gallium oxide is going to store more temperature. So it's going to be even worse. Yeah, it's going to be big challenges, I think, for reliability. But we're not near that yet. I think at the moment it's device architecture. Like your second question, what type of device structure do we need to create a low resistance 10 kV device, right? That's the question. That's what the jury's out, I think, on that. I don't know if that answers your question. I don't know.
No.
Yeah.
So any other question?
And what about the frequency, the dynamic behavior of the switch, this kind of switch? How much frequency we get for
in gallium oxide?
In gallium oxide, yes. 10 kV,
yeah,
and low resistance, as you said.
Yes.
How much frequency we get?
Okay, so I think if you have conventionally in silicon, for instance, right, if you have a bipolar device like IGBT or Thyrista, those very high voltages, they switch very slowly, right? And the first thing is, usually at the high voltages, you don't need high frequency. You're talking about grid level applications, so 50 hertz, 60 hertz, right? But so if it's a bipolar device, if it's a heterojunction type device in gallium oxide, which is injecting holes, yeah, or into the N type gallium oxide, you're going to have to remove those holes. And I think with a heterojunction as well, you get you get conduction band offsets, right, between one material and another material, and a depletion because of that, right? I think that's right. You can get a depletion, it's like a metal semiconductor junction in a way, right? Therefore, if you have additional depletion regions in the device, depletion region is like a capacitor, yeah? So you have a higher input capacitance as well. So I think, I think the switching frequency, I can't give you numbers, I have no idea. but I think it's going to be quite low frequency, yeah. Low switching frequency.
Okay, Mike, I think thank you again.
problem.
We can.